Hi and welcome to this Leaving Cert higher level algebra revision video. In this video we're going to look at abstract inequalities, which is inequality proofs. So the main idea here is that we want to always get the inequality down to a real number squared or multiple real numbers squared. The idea behind this is that we know no matter what the real number is, once we square it, it will definitely be positive. So this idea of any real number squared is greater than or equal to 0 because the real number could be a 0, and that's going to be the logic to solve every single one of these questions. Now some of these questions are quite challenging and we have to really work with our shortcut for squaring. So just a really quick reminder here that when we square a bracket, so a plus b to be squared, the correct way to do that results in 3 terms. So this one here, this is incorrect. So one of the most common errors I see. So it's not a squared plus b squared. It is a squared plus 2ab plus b squared. And the reason for that is if I square the bracket, what I'm doing is I'm multiplying the bracket by itself, and what we would usually do then to do that multiplication is we would split the bracket. So working that through gives me an a squared plus ab plus b squared, which gives me my a squared plus 2ab plus b squared. So this piece we're going to be doing today will really be starting with this and working backwards. So example 1, prove that a squared plus 2ab plus b squared is greater than or equal to 0 where a and b are element of real numbers. So this is quite straightforward because this left hand side here can be written as a bracket squared straight away. So this is a plus b squared is greater than or equal to 0. So how we'd usually finish this is therefore a squared plus 2ab plus b squared is greater than or equal to 0 since any real number squared is greater than or equal to 0. So that's going to be our kind of finishing line on all of these. Example 2. Prove that a squared plus 2ab plus 2b squared is greater than or equal to 0. So we were working in the last example with a squared plus 2ab plus b squared, which could be written as a plus b squared. Now here we have a plus 2b squared. So how we'd actually deal with this is quite simple. We take out what we need, so the 2ab plus b squared that we need to make that square bracket, and we leave a plus b squared then at the end. So we've just separated out that 2b squared into the two individual pieces. Now why I've done this is because the first piece can be written as this bracket squared plus b squared. Now it's not a bracket squared, but it is a real number squared. So now what I have is I have a real number squared, which is definitely positive, and I have a b squared, which is definitely positive. When I say positive in this case, it could also be 0, so really greater than or equal to 0. So this whole thing works, and we can say that it is most definitely greater than or equal to 0. For all of this proving, we do need to explain the logic as to why. So we say therefore, go back to the original statement, a squared plus 2ab plus 2b squared is greater than or equal to 0 since, and you only need to say it once, any real number squared is greater than or equal to 0. Example 3, so prove that for all real values of x, x squared minus 10x plus 25 is greater than 0. Now you might find it easier to work with these as they have numbers, so let's take a look. Can this be written as a bracket squared? So to do that, we would generally look at the square root of the first term, which is x, and we would have the coefficient of the second term, which would end up as minus 5 squared, and then we would generally double check this. So x squared twice the first by the last, so minus 10x plus 25. So yes, that's perfect. Greater than or equal to 0. Therefore, x squared minus 10x plus 25 is greater than or equal to 0, since any real number squared is greater than or equal to 0. Example 4. Prove that for all real values of x, 4x squared plus 12x plus 11 is greater than 0. So we don't have an or equal to this time. So we can approach this in two different ways. So the first one is to work with this like we've worked with all the other ones and try to write it as a bracket squared. The second way is to work more like the way we would work if we were doing completing the square or vertex form. The difference is when you're doing completing the square or vertex form, you must pull out that coefficient, that 4. When we're working with these kind of proofs, you don't have to. I'm going to show you both ways. So the first thing I do to make my bracket squared is I look at that 4x squared and I square root it. So I get 2x. Now, this is where it deviates slightly. Usually it's half of the coefficient of the x term, but really what we're trying to do is multiply 2x by something, then double it and get 12x. The easiest thing to do is to still have that coefficient of x, so it gives me a plus 6. And I look in my brackets and I say, well, 2 by what will give me my plus 6? And the answer is plus 3. Now, while you're getting used to that, always double check what your bracket has given you. So 2x squared gives me 4x squared. 2x by 3 is 6x and double it, so that gives me my plus 12x. So that's perfect. And when I square the last, I get a plus 9. Now, I actually have a plus 11 in my sum, but my bracket has only given me a plus 9. So I'll need an extra plus 2 to correct this is greater than 0. So what I'm working with is 2x plus 3 squared, which is definitely greater than or equal to 0, plus a 2. So even if this bracket was 0, we know that that bracket would end up being brought up into being, if it was a 0, it would be brought up to 2. So this is true. Okay, because this is true. Therefore, 4x squared plus 12x plus 11 is greater than 0, since any real number squared is greater than or equal to 0. So we have a number that's greater than or equal to 0. We add a 2, and that number has to be greater than 0. So example 5, prove that for all the real numbers p and q, this is true. So p plus q squared less than or equal to 2 times p squared plus q squared. Anytime you are dealing with an inequality proof, you want to go back to the idea that any real number squared is greater than or equal to 0. What that means for us is not just making the bracket squared, because we have one of those here already, but we want the right hand side to be a 0. So what we're going to do is we're going to expand out all of our brackets, move everything over to one side, and then see what we have. So squaring out this bracket, I get p squared plus 2pq plus q squared is less than or equal to 2p squared plus 2q squared. Moving everything over, I get p squared minus 2p squared plus 2pq plus q squared minus 2q squared is less than or equal to 0. Cleaning this up, I get minus p squared plus 2pq minus q squared is less than or equal to 0. Now, all the signs are incorrect because we would be looking to have a positive p squared, a positive q squared, and the fact that it's a less than or equal to 0 rather than a greater than or equal to 0. So what we're going to do here is we're going to change the signs. But remember, when we change the signs, we also need to change the inequality. which means it flips. So instead of being a less than or equal to 0, it becomes a greater than or equal to 0. So I get positive p squared minus 2pq, positive q squared greater than or equal to 0. And this is simply p squared, no, apologies, p minus q all to be squared greater than or equal to 0. The minus coming from the fact that this middle term here is a negative, and you can double check that. So that is true. So therefore, go back to our original, p plus q squared is less than or equal to 2 bracket p squared plus q squared, since any real number squared is greater than or equal to 0. So example 6, here we have a mock question of how this could come up. So I'm asked first of all to write the following as a single fraction. So it's not an equation. I can't get rid of the fractions. Instead, I have to use a lowest common denominator. In the majority of cases, so when we have two terms that have no common factors, the lowest common denominator is simply all the denominators, in this case both denominators, multiplied together. So 1 over x, to make that the common denominator of 2xy, I multiply the denominator by 2y and the numerator by 2y. Plus 1 over 2y, to make that a common denominator, denominator by x, numerator by x. So what I end up with is 2xy on the bottom and 2y plus x on the top, so in the numerator. So the next thing, part 2 then says, hence or otherwise, show that this thing, which is greater than or equal to, show that this expression is x plus 2y times 1 over x plus 1 over 2y is greater than or equal to 4. So notice where that hence is coming from. We have the fractions here. So I'm going to use what I had. So I have x plus 2y times, instead of that fraction, I'm going to have 2y plus x all over 2xy is greater than or equal to 4. Now, what's interesting about this question is they've told us here that x and y are greater than 0. That's really, really important. Effectively, what we have here is a rational inequality. So the rational inequalities we always have to be very careful with. Usually inequalities act like equations, so we can add numbers to both sides, subtract numbers, multiply, divide. But if there is a change of sign, and in particular if we multiply by a negative, which would change the sign, we will have to change the inequality. The problem with rational inequalities is that usually the denominator is a variable, an unknown, which means we don't know if it's positive or negative, which it adds a layer of complication to our sum. Here, they've taken away that layer of complication. So they've said x, y greater than 0. So I know that x and y are both greater than 0. They're both positive. So I do not have to worry about multiplying by x and y because it will not change the sign of the inequality. So the inequality itself will not change. So here I'm going to multiply out my fraction. So here I have x plus 2y times 2y plus x, so I'm squaring it, all over 2xy is greater than or equal to 4. To get rid of my fraction, I multiply simply by the denominator, not by the denominator squared. There's no need because I do know my denominator is positive because I have a positive by a positive by a positive. So I end up with x plus 2y squared is greater than or equal to 8xy. And this is more like we're used to. So let's expand the left-hand side. We get x squared plus 4xy plus 4y squared is greater than or equal to 8xy. Let's bring that 8xy across so we have our 0. That gives me a plus 4xy. Take away the 8xy plus 4y squared is greater than or equal to 0. So we get x squared minus 4xy plus 4y squared is greater than or equal to 0, which can be written as a square bracket. It is x minus 2y to be squared is greater than or equal to 0. And we know that is true because any real number squared is greater than 0. So therefore, x plus 2y times 1 over x plus 1 over 2y is greater than or equal to 4, since any real number squared is greater than or equal to 0. Example 7. So a lot of these questions that we've been practicing have been quite straightforward in what they've been asking. They've given us the inequality and they've asked us to prove that it is true. It is more likely in an exam situation that we won't be given a question like that, but given something like this. So it says, prove that this equation has real roots for all values of p element of R. So what we're talking about here is really a quadratic function, and we're trying to prove that it has real roots, and we're going to do that using the discriminant. To use the discriminant, we'll end up with an inequality that we will then have to prove. So as a reminder, the discriminant is the piece of the quadratic formula, the minus b formula, that's underneath the square root. So b squared minus 4ac. So we have a few scenarios for this. We have b squared minus 4ac is greater than 0, gives me 2 real roots. If it is equal to 0, it has 1 real root. It still has 2, but it has 1 distinct real root. And then if it has no real roots, it is less than 0, so no real roots. And we will be looking at in the imaginary and complex number section that third scenario. But for this question, it didn't say how many, it just said real roots. So in order to work with that idea of real roots, we end up combining the first two scenarios here. So to prove that they have real roots, we're going to have b squared minus 4ac is greater than or equal to 0. So it's a combination of those two. So let's figure out what a, b, and c is first. So a, b, and c. So in your equation, it is ax squared plus bx plus c equals 0. And that is from page 20 of your log tables, where it'll give you that quadratic. A is the coefficient of x squared, which is p. B is the coefficient of x, which is minus 2p plus 1. And c is, c is 2. So b squared, which is minus 2p plus 1 squared minus 4 times a times c. Now, when we're squaring the negative, it'll become positive. So minus by a minus will be a plus, so I can simply square the inner bracket. However, you can happily multiply in that negative before you're squaring. So it's this one here. So minus squared will end up positive. So that's what this whole section has been about. Any real number squared will be positive, so even if it's negative. So this works out as 4p squared plus 4p plus 1 minus 8p is greater than or equal to 0. 4p squared minus 4p plus 1 is greater than or equal to 0. I can now write this as a bracket squared, which is 2p minus 1. The reason it's a minus, again, is this middle term is negative. And that is true, and we just need to finish with our statement. So therefore, now we're not going to go back to our initial statement this time. We're going to say, therefore, the equation has real roots since any real number squared is greater than or equal to 0. So this is more likely the way we will see it. We'll have to set up the inequality ourselves. And there's a few different ways you could set up an inequality, but probably the most common will be the use of discriminant.